Hello, I thought I'd go through Module 7, which is about simulating cells in a Petri dish. Okay, so the key part of this is it's about object orientation. So we first of all have a cell. Let me just make that a bit bigger and get rid of the other stuff. There we go. Right, so we have a cell class and it has a static member variable count. That static means that it's associated with the class rather than a specific instance of the class. A member variable is usually prefixed with self, right? So each individual instance can have a different X, a different Y, a different lifetime, and a different symbol, but the count is across all members of type cell, all objects of type cell. That's why we prefix this increment with cell rather than self. Okay? And we use the keyword static method in order to be able to access this method reduce count as a static method rather than just a method on each member or each instance. And then we're going to make a generic cell which derives from cell but is called generic, and we're going to make an E. coli one, we're going to make a structure one, and we're going to make a hunter-killer one. Okay, so the first thing to do is we need to place a cell in the Petri dish, and we need to complete the add to world method on the Petri dish class. I didn't have a look at the Petri dish class, but it's down here, right? And my implementation of the add to world method looks like this. And first of all I create the cell location because the cell has an X and a Y, right? So this class, the Petri dish class, takes a cell object as input and does three things. First, it should be noted the Petri dish class contains a dictionary called self.world, which is a mapping of a Petri dish coordinate to a symbol of a cell occupying the space. Use the XY coordinate information of the cell to populate the Petri dish map with the symbol of the cell. Secondly, the Petri dish also has a list of cells, which is the all cells, which it uses to keep track of all alive cells, and the new cell needs to be added to the list. Finally, as a preventative measure, we need to keep track of all the free positions, and there's an available positions, self.available positions list, and we need to check that that's currently free. When the Petri dish is created, the self.available positions list is completely full with all possible positions, but as you add them, it's going to be removed from the list. So how did I do that? Well, I got that cell location, and if the cell location is not in the available positions list, then I'm throwing an error. I don't know what to do in that case, so I'm just going to throw my hands up and throw an error. But if that's not true, then I can put the cell symbol into the world at that location. I can then remove that location from the available locations, and I've got the cell, so I can just append it to the list of all cells. And we're good. And as you can see, I think I got task 1 running. And once that's done, it wanted us to create a Petri dish of size 30, add four cells at positions 0, 0, 5, 5, 10, 10, and 15, 15, and then begin the simulation. So there we go. Let's have a look at that. Oops. That's right, I can't copy from there for some reason. So let's go back down to the bottom. It's activity 1, task 2. Right, so this is what I did. I create the Petri dish of size 30. I add the cells of the appropriate location, 0, 0, 5, 5, 10, 10, and 15, 15. I then call that method add to world that I wrote with each of the cells that I just created, and then I started the simulation. Okay, so, and I got a check mark for that one. The next one was to create a Petri dish of size 30, and then using random.choice, create and add 10 cells to the Petri dish. Right, so I did that again in task 3. So there's my 30 cell Petri dish, and then I did just arrange over 10, so to get 10 things, and then I use the choice method on Petri dish.available positions. I create a new cell at that location, and then I add it to the Petri dish. And because I wrote that add to world method earlier, it'll remove this randomly chosen location from the from the available positions list. Okay, and I think I got that one right too. The next thing is to extend the classes, right? And the only difference between the cell class and the generic class is the symbol is now an O instead of a C, I think it was. So let's have a look at what I did for that. So here's the symbol, the method that sets the symbol for the cell class, the base class. And for generic, I just changed that implementation to return an O rather than a C. So that's what that did. And then activity 2, task 1. Let's have a look at that. Activity 2, task 1, same size Petri dish, 10 cells, choose some cells, add generic cells now to the world, and begin the simulation. And that was all fine. And then do the same thing for the E. coli class, and now the symbol is just an E. Right, so same thing, but now instead we've got the E. coli. And let's check the implementation of the E. coli class. So set symbol is just returning a small e. A structure class, same thing again, except this time I think it's actually a capital S. That confused me a bit before. I had small s and it failed, but so it needs a capital S. So just be careful with that. There wasn't any other changes to that. And then the hunter-killer class was a small x, and again I just changed the symbol implementation to that. Now, activity 2, task 5 was to add 10 instances of cell, generic, E. coli, structure, and hunter-killer at randomly allocated positions. And it wants us to do it in a particular order. First of all, 10 cells, then 10 generic, then 10 E. coli, then 10 structure, then 10 hunter-killer. I believe the reason it's doing that is so that it's quote random, and this is pseudo-random because we're using a seed to start things off, will match what it's expecting. So you need to do them in that particular order, batches of 10 rather than iterating through 10 batches of 1. Okay, and let's have a look at that. That was activity 2, task 5. Activity 2, task 5, right? So 30 by 30 Petri dish, range 10 for cell, generic, E. coli, structure, hunter-killer, and then begin the simulation. And that one worked. Then we needed to count the different types in activity 3, task 1, right? And we're going to add 10 generic, 20 E. coli, and 30 hunter-killer. And then we need to not start the simulation, because if you start the simulation, some of the cells die. And that was confusing me a bit because I just cut and paste my previous implementation. But in this one, you don't want the begin simulation. And how do we do that? Well, what we've got to do, remember I talked about this before, this is the static variable count, and we need to add a static variable count to each and every class derived from cell if we want a separate count, and then we need to increment that particular variable in the constructor of each of those. So we keep a specific count of each individual type of cell, and then up in the base classes count we'll keep a count of all possible types of cells, right? So you get a much bigger number in the cell count than you do necessarily in the generic or E. coli numbers. Okay, so that's that one. Then it wants us to just do a reset on all counts, and there's a couple of ways to do this. Reset all cell counts. It started off with a list of all the cell types, so I just thought, well, let's just iterate through those cell types and call count on each of them. And that's a quick and easy way. You could also just say cell.count equals 0, generic.count equals 0, E. coli.count equals 0, structure.count equals 0, and hunter-killer.count equals 0. Iterating through is a little simpler, a little easier. Plus, if you add another different type, it's just a matter of adding to this list of cell types rather than having to remember to change the count. Then we wanted to add a static method, right? Remember, a static method is associated with the type rather than a particular instance of the type. So here the cell method has that, and it decrements cell.count. So I just did the same thing for generic, decrementing generic.count, and E. coli decrementing E. coli.count, etc., etc. Okay, so they all get reduced. Then it was just a matter of changing lifespans, and again it was similar to the symbol change. The lifespan is using _set _lifespan. So I didn't really have to change this one because it's the same as the base class, but I thought I'd better do it anyway. and 7 is for E. coli, and 10,000 was for structure, and 350 was for hunter-killer, which is the numbers there, so I did that. And then activity 3, task 4. For some reason I can't get that one to run. I don't know what I'm doing wrong there. It just decided not to run. And then task 12 was about updating the intended position method for at least the generic and the hunter-killer. Right. And the way I did that, the generic, it has to be X and Y. It changes from the current position to a new position, be randomly chosen between -2 and 2 in X and -2 and 2 in Y. So I just did a range of -2 to 3. Remember that last item, the stop number is not included in the range. So in order to get -2, -1, 0, 1, and 2, you need to set that upper range, upper limit to 3. Okay, and I got update to X location, update to Y location. I'm using the random.choice method. And then I'm just adding the X update to X and the Y update to Y in order to move it. And similarly the hunter-killer, but now I'm going -1, 2 for the range, and then just doing the same update. Okay, and I think I did that. Let's see if it runs. Right, it's kind of cool. It kind of does a little bit of an ASCII animation there, and that was pretty much it. So that was mainly about changing the deriving classes from a base class to make the behavior of the derived classes just a little bit different from the base class, and also keep track of specific numbers of each of the different types of base class. Anyway, I hope that's helpful. I will also be continuing probably later this week with Module 8 and a Module 9 project video.